All right, so get this. You know how everyone thought the expansion of the universe was like slowing down, after the Big Bang?
Yeah.
Turns out they were wrong.
Uh-huh.
It's actually speeding up.
Yeah.
And today's deep dive
Yeah.
is all about figuring out why.
Exactly.
Good.
We're going to be looking at a paper from 1998
Okay.
from the High-z Supernova Search Team.
Cool.
They used these incredibly bright stellar explosions called type Ia supernovae
Uh-huh.
to uncover this mind-blowing truth about the universe.
Okay, so exploding stars are giving us clues about, like, the fabric of space-time.
Yeah.
I'm intrigued.
It all starts with this cosmic puzzle.
Okay.
Scientists knew the universe was expanding,
Right.
but they kind of expected this expansion to be slowing down because of gravity.
Makes sense.
Yeah, think of it like tossing a ball straight up in the air.
Yeah.
You'd expect it to eventually slow down and fall back down, right?
What goes up must come down.
Exactly.
Yeah.
So the thinking was that the universe filled with matter should behave similarly.
Okay.
But here's where the supernovae come in.
Okay, so how did these supernovae throw a wrench in that whole slowing down idea?
Well, astronomers were observing these distant type Ia supernovae,
Right.
and they were expecting them to be a certain brightness based on how far away they were. But they found something shocking.
What?
The supernovae were dimmer than expected.
Dimmer.
Yeah.
So what does that tell us?
It means they were farther away than they should have been if the expansion was slowing down.
Oh.
Imagine you have a light bulb.
Okay.
The farther away you move it, the dimmer it appears.
Yeah.
The same principle applies to these supernovae.
So it's like the universe's expansion had this sudden growth spurt,
Yeah,
pushing those supernovae farther away.
precisely.
Okay.
And that's how they concluded that the universe's expansion wasn't slowing down, but
Right.
speeding up.
Hold on a second. So we're talking about something that makes up like the majority of the universe,
Yeah.
and we have no idea what it is.
Yeah,
That's wild.
that's the big mystery.
But how did they even use supernovae to measure the expansion in the first place?
That's where the idea of luminosity distance comes in.
Okay.
So type ES supernovae have this remarkable consistency in their peak brightness.
Okay.
They're like cosmic light bulbs with a known wattage.
Uh-huh.
Astronomers call these standard candles.
Yeah.
By comparing the observed brightness to their known intrinsic brightness,
Right.
we can calculate their distance.
So it's like those brightness controls on your phone screen.
Yeah,
The farther away the supernova, the dimmer its light appears to us.
you got it.
Cool.
And by tracking how this distance changes over time, we can measure how fast the space between us
Okay.
and those distant supernovae is expanding.
Clever.
Yeah.
But the paper mentioned like two methods they use to analyze the supernova,
Yeah.
MLCS and M15b.
Mm-hmm.
Why were these so important?
Those methods help refine the distance calculations.
Okay.
So while type ES supernovae are remarkably consistent, there are subtle variations in their light curves, how their brightness changes over time.
Gotcha.
These methods take those variations into account.
So it's like double checking their work
Yeah,
to be extra sure about the distances.
exactly.
There.
And these extra precise measurements made the conclusion about the accelerating expansion
Yeah.
even stronger.
Wow. So it's like there's this invisible hand pushing the universe apart.
Yeah.
That's both terrifying and fascinating.
Yeah, it is a big mystery.
But what could this mysterious force be?
Well, the researchers knew it couldn't be regular matter like galaxies and stars.
Right.
Because that should be slowing the expansion down.
With its gravity, yeah.
Yeah.
Okay.
They realized that the observed acceleration required something else entirely,
Uh-huh.
something they called the X component.
So they found that the universe's expansion was being driven by something unknown.
Yeah,
That's a lot to process.
it is.
Okay.
Imagine a giant cosmic tug of war.
Okay.
On one side, you have matter, trying to slow things down with its gravity.
Makes sense.
But on the other side,
Uh-huh.
you have this mysterious X component pushing outwards and winning the cosmic tug of war.
Okay, so we've got this X component pushing things apart.
Yeah.
But how do we even begin to describe that scientifically?
They used what's called the equation of state,
Okay.
which describes the relationship between pressure and energy density.
Right.
Think of it like a spring.
Okay.
If you press it down, it pushes back against you.
Yeah.
That's like positive pressure.
Okay.
Dark energy, however,
Mhm.
is like a spring that pushes back outwards when you compress it.
Okay.
That's negative pressure,
Negative pressure.
which sounds strange,
Yeah.
but it's needed to explain the accelerating expansion.
It is a bit mind-bending, isn't it?
It is, yeah. It's
Yeah.
a lot to wrap your head around.
It really is.
Yeah.
So by analyzing the data from those 50 supernovae, Did the team figure out what this X component, this mysterious force, actually is?
Well, they were able to narrow it down. So some of the supernovae they observed date back to a redshift of Z1.
That sounds really far away.
It is the light that we see from those supernovae left them billions of years ago.
Wow.
So we're essentially looking back in time to the deep past of the universe.
That's incredible.
And what they found is that it's highly unlikely that ordinary matter alone could explain those observations.
Okay.
Something else had to be at play.
So what were some of the contenders for this mysterious something else?
They considered a few possibilities. One idea was these things called topological defects.
Topological defects.
Yeah, imagine them as like wrinkles in the fabric of space-time.
Cosmic wrinkles, huh?
Yeah, left over from the very early universe.
What do those even look like?
Think of them as like cracks or knots in the structure of the universe.
Okay.
And that could have a lot of energy density, potentially enough to impact the expansion.
Interesting. So they were looking into whether these cosmic wrinkles could be the culprit behind the acceleration.
Yes, but their analysis showed that the data didn't really support that idea.
So if it wasn't these cosmic wrinkles, what else could it be? Did they find anything else that fit the bill?
Their attention turned to something Einstein himself had proposed decades earlier.
Okay.
The cosmological constant.
Wait, isn't that the thing that Einstein called his biggest blunder?
Yeah, maybe not so blunderous after all.
Okay.
It's this idea of a constant energy density that's just built into the fabric of space itself.
So like a kind of energy that's everywhere all the time, even in like a perfect vacuum.
Exactly.
That's a lot to wrap my head around.
It is. It is. And what the researchers found is that their data from the supernovae was consistent with the cosmological constant, or something that behaves very similarly, which they called quintessence.
Quintessence. That sounds almost mythical.
Yeah.
So is this the same thing as that X component that they mentioned?
Yes.
Okay.
Dark energy is the name that's stuck for this mysterious force.
Okay.
It's called dark because we can't see it directly,
Right.
and we don't really know what it is,
Yeah.
but it seems to make up a large part of the universe's energy budget.
Okay. I think I'm starting to get a handle on this. We've got dark energy, possibly in the form of this cosmological constant or quintessence,
Right.
driving the accelerating expansion.
Yeah.
What else do they look at in this paper?
They also brought in information from another important source, something we've talked about before, the cosmic microwave background.
Right, like the baby picture of the universe.
Exactly.
Yeah.
And the pattern of tiny temperature fluctuations in the CMB, its power spectrum,
Okay.
can help constrain different cosmological parameters, including the density of matter and dark energy.
So they combine the data from these exploding stars with this baby picture of the universe.
Yeah.
That's an incredible combination.
It is, and what they found is that the combined data strongly supported a universe that's not only accelerating in its expansion,
Okay.
but is also spatially flat.
Wait, a flat universe. Does that mean it's like a giant sheet of paper?
It's more nuanced than that,
Okay.
but in essence, yes.
Okay.
Imagine a triangle drawn on a flat surface.
Yeah.
Its angles will add up to 180 degrees.
Right.
In a flat universe, the same rules of geometry apply on a cosmic scale.
I see.
A curved universe would have different rules.
Okay.
And all of this seems to point towards a universe dominated by this mysterious X component, or dark energy.
This is so much to take in.
It is.
It sounds like the team was really thorough in their investigation.
Yeah.
But they also mentioned something called the null energy condition. What's that all about?
The null energy condition, or NEC, is like a set of rules that energy and matter have to follow in space-time, even exotic things like dark energy.
Okay.
It basically says that energy density can't be arbitrarily negative.
So it sets a limit on how weird this dark energy can be.
You could say that, and what's fascinating is that even with the acceleration, the supernova data seems to respect the NEC.
Interesting.
It suggests that dark energy, whatever it may be, still plays by the fundamental rules of physics.
But there's always, but in science, isn't there?
Of course, there are some theoretical models, particularly with certain types of quintessence, that suggest it might be possible to violate the NEC under very specific circumstances. But that's getting into pretty complex territory.
Okay, let's stick with the basics for now.
Yeah.
So we have this mysterious dark energy. Maybe in the form of the cosmological constant or quintessence.
Right.
Driving the accelerating expansion of the universe. What other big questions about dark energy did this paper raise?
Well, one of the most important ones is about its equation of state.
Okay.
Remember how we talked about dark energy acting like a spring that pushes back outwards?
Right, yeah.
The equation of state helps us quantify this behavior and understand how dark energy affects the universe's expansion.
So figuring out this equation of state would give us more clues about the nature of dark energy. What kind of experiments could they do to figure this out?
There are a number of ambitious projects going on right now.
Oh, cool.
For example, telescopes like the Vera-Rubin Observatory are designed to survey huge sections of the sky, looking for even more distant supernovae to create a more detailed map of the universe's expansion history.
So it's like making a time-lapse video of the expanding universe with dark energy as the star of the show.
That's a great way to put it.
Awesome.
And by studying how dark energy's influence has changed over billions of years, we can get a better understanding of its properties.
That sounds amazing.
Yeah.
Are there any experiments specifically looking into this idea of quintessence?
There are quite a few.
Oh, cool.
They're looking for subtle variations in the strength of dark energy across different regions of space or over time.
So if they find these variations, it would mean that dark energy isn't just a constant force, but something more dynamic and complex?
Precisely. It would be a major point in favor of quintessence and open up even more intriguing questions about what this dark energy really is.
Wow. This is also fascinating. I'm starting to see why this paper was so groundbreaking. It wasn't just about discovering the accelerating expansion, but also about opening up this whole new frontier of research into dark energy. Anything else in the paper that we haven't covered yet?
There's one more point they briefly touched on that I think is worth discussing.
Right.
They entertain the possibility that maybe, just maybe, the acceleration isn't due to some mysterious dark energy that could be a sign that our understanding of gravity itself is incomplete.
Well, wait a minute. Are you saying that gravity might not work the way we think it does on these vast cosmic scales? That's a pretty radical idea. Are there even any alternative theories about gravity that could explain this acceleration?
There are a few, but they get pretty complex and are still on the fringes of mainstream cosmology.
Right.
One idea is that perhaps gravity weakens at very large distances, or that there are other subtle forces at play that we haven't detected yet.
It's almost like the universe is saying, hey, you think you understand gravity? Think again.
It's definitely humbling to think that our current understanding of physics might not be the whole story.
Yeah.
But that's what makes science so exciting.
Right.
There's always room for new discoveries.
Absolutely.
And paradigm shifts.
Okay, so we've covered a lot of ground here.
We have.
We've explored the surprising discovery of the accelerating expansion.
Yep.
Learned about this mysterious force called dark energy. And even touched on the possibility that maybe our understanding of gravity itself needs some tweaking.
Yeah. It's a lot to think about.
It really is. What's the one big takeaway you want listeners to ponder after this deep dive?
Here's a question to consider. If dark energy truly is a fundamental property of the universe, could future discoveries about its nature lead to revolutionary technologies? Things like manipulating gravity or even traveling faster than light.
Wow, now that's a thought-provoking question.
Yeah.
It's incredible to think that something as seemingly abstract as dark energy could have such profound implications.
It really highlights the importance of basic research.
Yeah.
We often don't know where it will lead.
Right.
But history has shown us time and again that pursuing knowledge, even in the most esoteric realms of science, can lead to unexpected and transformative breakthroughs.
Well said. To our listeners, thanks for joining us on this journey to the edge of the cosmos. Keep those minds curious and never stop exploring the wonders of the universe.